Every emergency radio you rely on will eventually fail. Every battery you store will run out of life. Even solar panels can be damaged, stolen, or covered by snow. But in 1901, Nikola Tesla introduced an idea that challenged all of that. He showed that a simple loop of wire, not connected to any traditional power source, could draw energy directly from the electromagnetic radiation already present in the air. At first, power companies dismissed it as impossible. Later, they called it unsafe. Eventually, the idea faded from public attention. So what did Tesla really uncover? All around you, energy is constantly moving. Radio stations, cell towers, Wi-Fi routers, and even the electrical wiring inside buildings continuously emit electromagnetic waves. Each wave carries a small amount of energy. Individually, it is tiny, but it never stops. It surrounds you at all times, and it does not cost anything to exist. A simple wire loop can act as an antenna. When electromagnetic waves pass through it, they create a small alternating current. This is the same principle that allows your car radio to work. The radio is not producing energy, it is capturing signals that are already there. In a way, your car radio has always been collecting ambient energy. You just never noticed it from that perspective. Tesla's patent, number 685,957, filed on February 19, 1901, described a method for using radiant energy. The concept was straightforward. An elevated metal plate connected to a capacitor. The plate absorbs electromagnetic energy from the environment, and the capacitor stores it. Once enough charge builds up, it can be released to produce light, heat, or motion, all from the invisible energy already present in the air. His design showed a polished metal plate mounted on an insulated structure, connected to one side of a capacitor, while the other side was grounded. As radiation reached the plate, it slowly charged the capacitor. When the voltage became high enough, the stored energy discharged through a small gap or switching device, powering whatever was connected. Tesla demonstrated this using a small lamp, and it lit up, without batteries, generators, or direct wiring. Just a metal plate and stored energy from the environment. The science behind this is well understood. Maxwell's equations, published in 1865, explain how electromagnetic waves behave. These waves contain electric and magnetic fields that constantly change. When they meet a conductor, they cause electrons to move. That movement is electric current. And when current flows through a material, it can produce heat, light, or motion. The energy was always there. Tesla simply showed a way to capture it. Modern versions of this idea can be even simpler. A small coil of copper wire, about 50 to 100 turns and roughly 6 inches in diameter, can act as a loop antenna. Its size helps it respond to certain frequencies. When you connect both ends to a germanium diode, the alternating current is converted into direct current, allowing energy to build up in one direction. Add a small capacitor, around 10 microfarads at 25 volts, and you now have a basic storage system. The total cost can be less than $2, using inexpensive parts like magnet wire, a diode, and a capacitor that are easy to find. The choice of diode matters. Silicon diodes are common, but they require about 0.6 to 0.7 volts before current can pass through them. Signals collected from ambient radiation are often much weaker than that. Germanium diodes, however, only need about 0.2 to 0.3 volts. That lower threshold makes them far more effective for capturing small amounts of energy. In this setup, the difference is critical. One works, the other may not. Real-world testing shows how this behaves. Near an AM radio tower about 1 kilometer away, such a loop can produce between 50 and 200 millivolts, depending on conditions. Close to high-voltage power lines, the voltage can reach 500 millivolts or more due to stronger electromagnetic fields. Around a Wi-Fi router, a properly tuned loop can continuously capture small amounts of power in the microwatt range. That may not seem impressive at first. But the key is not immediate output. It is steady collection over time. Think of it like rain. One drop does nothing, but steady rainfall can fill a container. In the same way, small amounts of harvested energy can build up. Over a day or two, A storage device like a supercapacitor can collect enough energy to power a brief transmission. This opens the door to interesting possibilities. Imagine a simple emergency beacon that never depends on batteries. A device that continues to gather energy quietly, even when everything else fails. When needed, it releases that stored energy to send a signal, powered only by the invisible energy that already exists all around us. Let's break down how an emergency RF energy harvesting beacon can actually be built. Start with a coil made from 100 turns of 28-gauge enamel-coated magnet wire, wound around a form about 4 inches in diameter. You can use a PVC pipe, a cardboard tube, or even a tightly rolled magazine. This coil will typically have an inductance in the range of 300 to 500 microhenries. When paired with a variable capacitor between 100 and 500 power factors, it can resonate within the AM broadcast band, allowing it to capture energy more effectively. Next, connect the coil to a Schottky diode. Compared to germanium, Schottky diodes perform better at higher frequencies and have even lower voltage drops. For example, a BAT46 diode has a forward voltage of around 0.15 volts and is extremely inexpensive when bought in bulk. This low threshold allows even weak signals to pass through and be converted into usable direct current. From the diode, route the output into a 1 farad, 5.5 volt supercapacitor. This acts as your energy storage. The capacitor charges gradually as it collects energy from the surrounding electromagnetic waves. To protect the system, you can include a simple charge control circuit using a Zener diode and a transistor, which prevents the capacitor from exceeding safe voltage levels. Once the stored voltage reaches around 3.3 volts, there is enough energy to briefly power a low-consumption microcontroller such as an Atiny-85. For a few seconds, the system can wake up, perform a task, and then shut down again. In that short window, it could read data from a GPS module and transmit a small burst of location information over a license-free frequency. All the components together cost roughly $8. The result is a device with no batteries to replace, no solar panels to maintain, and no moving parts. It quietly collects energy already present in the environment and uses it when enough has accumulated. In theory, such a system could operate for very long periods with minimal intervention, transmitting small packets of data at intervals. This concept is not entirely new. Research programs, including DARPA's Wireless Ambient Radio Power, WARP, initiative, explored similar ideas. Universities like Georgia Tech, MIT, and Duke studied how remote sensors could run on ambient RF energy alone. These systems demonstrated that low-power devices could harvest energy from nearby transmitters, such as cell towers, and use it to send back simple data like temperature or motion readings. However, there are practical limits. The amount of energy available from ambient RF sources is extremely small and varies widely depending on location and surrounding infrastructure. While such systems can power ultra-low energy electronics intermittently, they cannot replace conventional power sources for anything demanding continuous or high power. A classic example of this principle is the crystal radio. For over a century, hobbyists have built radios that operate without batteries or external power. Using a long wire antenna, a coil, and a diode, these radios convert radio waves directly into sound. The energy comes entirely from broadcast signals already in the air. It is a simple but powerful demonstration that energy can be captured from the environment. Even so, scaling this idea is challenging. Ambient energy harvesting works best for small, low-power applications where patience and efficiency matter more than output. It is useful for niche scenarios like remote sensing or emergency signaling, but it does not eliminate the need for traditional energy systems. A single-loop antenna only captures tiny amounts of energy, usually in the microwatt range. If you connect multiple loops together, the output can increase. 10 loops may push the total into the milliwatt range, and larger, well-organized arrays can collect even more. When these antennas are arranged carefully and combined with rectifying circuits, they form what is known as a rectenna, short for rectifying antenna. This setup converts captured electromagnetic waves directly into usable DC power. The concept of rectennas is not new. In 1964, Engineer William C. Brown at Raytheon demonstrated this idea by transmitting microwave energy at 2.4 GHz across a room and converting it into electricity with very high efficiency. He later expanded the experiment, successfully sending power over a distance of about 1 mile from a hilltop to a receiving station below. The results showed that wireless power transmission using directed energy was possible, and the system worked reliably under controlled conditions. Since then, the technology has continued to improve. Researchers have explored ways to make rectennas smaller, cheaper, and more efficient. In 2021, a team at Georgia Tech presented a design for a flexible, printed rectenna capable of harvesting energy from 5G millimeter wave signals. The entire system, antenna, rectifier, and basic power management, was produced on a thin, flexible material using printing techniques similar to those used in standard manufacturing. The goal was to power very low-energy devices, such as IoT sensors, without relying on traditional batteries. This shows that the idea is not just theoretical. It has been demonstrated in laboratories and research environments many times. However, there are important limitations. These systems typically rely on either very strong nearby signals or specially directed power sources. Ambient signals alone usually do not provide enough energy for anything beyond small, intermittent tasks. There are also larger-scale concepts being explored. For example, Japan's space agencies have been researching space-based solar power systems for decades. The idea is to collect solar energy in orbit and transmit it to Earth using microwaves, where ground-based rectenna arrays would convert it back into electricity. Projects like those proposed by JAXA aim to make this approach viable in the future, though significant engineering and economic challenges remain. Across all these examples, the core principle stays the same. Electromagnetic energy can be captured and converted into electricity. The technology has been proven in specific contexts, especially where conditions are carefully controlled or power is intentionally transmitted. But in everyday environments, the available energy is limited, which is why these systems are mainly used for specialized, low-power applications rather than replacing conventional power sources. Your version does not rely on space-based transmitters or advanced infrastructure. It does not even require 5G towers, although they can help. It works using only the electromagnetic energy that already exists in your surroundings. Now here's how that idea can be applied in a practical survival setup. Start with Step 1. Building a crystal radio for emergency reception. Stretch a long wire, about 50 to 100 feet, between two elevated, like trees. The higher you place it, the better the reception. Run this wire into a coil made of roughly 80 turns on a 3-inch form. Connect the coil to a germanium diode, then attach it to a high-impedance earphone rated at least 2000 ohms. Finally, ground the system using a metal rod driven about 12 inches into damp soil. This simple setup creates a radio that needs no batteries or external power. It can receive AM broadcasts from distances of up to 100 miles, and the total cost is around $5. Step 2 focuses on harvesting ambient energy for small devices. Wind 100 turns of 28-gauge magnet wire around a 4-inch PVC pipe. Connect the coil to a BAT46 Schottky diode. From there, pass the output through a 100 ohm resistor into a 1 farad, 5.5 volt supercapacitor. To improve performance, attach small aluminum foil plates, about 6 by 6 inches, to the top and bottom of the coil. These act as ground planes and help capture surrounding electromagnetic fields more effectively. Place this device near sources of radiation. Close to a power line, the 60 Hz field may charge the capacitor to around 3 volts in about 12 hours. Near a cell tower, it could take 1 to 2 days. If positioned within a few feet of a Wi-Fi router, charging may occur within several hours. Step 3 brings everything together into an emergency GPS beacon. Connect the charged supercapacitor to an ATINY 85 microcontroller through a voltage regulator. Program it so that once every 24 hours it powers on, reads data from a GPS module, and sends out coordinates using a simple 433 MHz transmitter. The transmission lasts less than 2 seconds and uses about 50 millijoules of energy. A fully charged supercapacitor at 5.5 volts can store over 15 joules, which is enough for hundreds of short transmissions before it needs to recharge. The total cost for this beacon setup is roughly $8. It has no batteries to replace, no fragile solar panels, and no moving components. It collects energy quietly from its environment and uses it only when needed. With basic tools and some electronics knowledge, it can be assembled in a single afternoon. The underlying idea has been known for more than a century. Simple versions, like crystal radios, have been built by hobbyists for generations. More advanced versions can power small sensors or send occasional signals. However, it is important to stay realistic about what this technology can and cannot do. These systems do not replace traditional power sources, and they cannot run large devices or homes. The energy available from ambient electromagnetic fields is limited and highly dependent on location. What they do offer is a different perspective. Energy is constantly moving through the environment, and with the right approach, small portions of it can be captured and used. In specific situations, like low-power sensing or emergency signaling, that can be useful. It is not about unlimited free power, but about making practical use of what is already present around you.